But this morning's event is for Francelino Rodrigues Jr. Francelino also works for CIMMIT, and he's worked for CIMMIT since 2013 as a postdoctoral fellow in precision ag and also currently an associate scientist in precision ag. His research experience is around agricultural engineering, focusing on precision ag and remote sensing, and very much at proximal sensing, as you'll see today. So he has skills in geostatistics, data mining and modeling, high-resolution crop and soil surveys. Francelino comes from Brazil. He did his undergraduate at the University of West of Parana, a master's in precision ag from University of Viçosa, and a PhD in precision ag at the University of Campinas. I got to know Francelino in 2010 when he joined CSIRO in Australia for a part of his PhD program, 6 months or 9 months, working with us on precision agriculture in our systems, looking at proximal sensing of salt and soil constraints for designing precision ag systems for our large broad acres farming systems. So welcome, and we are looking forward to your seminar.
Thank you. Thank you very much, Anthony. Well, good morning, everyone. Thank you very much for being here. And yeah, I'm glad to talk a little bit about this story that we've been building over there in Mexico. So as Anthony said, I'm pretty much into proximal sensing, and now I'm getting into the remote sensing technologies as well. All of them use it for crop management purpose. So I'll be talking a little bit about this data that we've been collecting there in Mexico, okay, and some preliminary results that we have been having, and some data mining as well, because it's so much data that it gives us opportunity to explore this data on infinite ways, right? Okay, so the project leader of this is Urs Schuttels. This is part of another project that is going on, which is STARS, and it's a project that ICRISAT has part of it, actually. And specifically on this presentation is how we can be using hyperspectral signal, hyperspectral imagery, to be understanding wheat yield spatial variability within a field, right? Okay, so just locating you guys where we are and where are the sites and everything. That's Mexico country. On this green spot here we have our headquarters from CIMMIT, and around 1,500 kilometers away in the north we have the Sonora state, which is the wheat region. It's like the main wheat region of Mexico. And over there we have in Ciudad Obregón we have a experimental station over there, where is the main station for wheat breeding. And as is the main region for wheat, the wheat growers, so we are having farmers farming experiments as well, and we are coming along with them and trying to improve crop management in terms of nitrogen management or water management using this kind of technology. So the importance of wheat for Mexico. We have this fall stats data, which is showing us like here, like wheat production on the red line was growing and the wheat area was getting down, which is quite good, okay. The average of Sonora state, the whole Sonora state on 2012 was a yield of 7 tons per hectare, and the area growed with wheat was roughly like 250,000 hectares. Mainly it's 80% is irrigated, so it's a really like dry area, is desert, and many of the wheat growing there is irrigated, and mainly is durum wheat as well. So we see that it's actually on a national scale, it's really important for wheat production. It's a really important region. And we also see that there is potential for building more, right? Using better the natural resource in terms of nutrient, in terms of water, and everything. Some related works on it. Actually, mainly these papers that I pasted here is mainly related with grain protein. And actually, we are interested also on the quality of the grain, not just on yield. So the idea is to explore how we can understand the spatial variability of yield and quality of the grain. And we have here some works from Australia, some works in China, using remote sensing or using proximal sensing to measure grain protein. And some papers here are already talking about selective harvesting, which is one of our goals actually. Is like how we can understand or how can we estimate the spatial variability of grain protein before harvesting. So that's like one of our goals. And this paper here specifically, they are approaching this kind of, they are talking about this kind of approach and giving it two options. Or we go for on-the-go measurement during the harvesting, where it's like if we talk about broad acre areas, it might be possible. Or we go for predicting this spatial variability before harvesting. And sure, there are some implications for that. They're saying that mainly if you have high yield, you're going to have a lower protein content concentration in the grain. But some other papers, they were investigating how this is within field, how is this within field spatial variability, and is not 100%. So we have case that we can have higher yields with higher grain proteins, and we can have lower yields with lower grain proteins. And there is a link with soil spatial variability as well. So how soil is holding water and how this is related with the grain. So summarizing, it's this, and we have some work with grapes as well, with Rob Brumley in Australia. Selective harvest of grapes according with the quality, and going for different, like making different wines in that case. So having like a profitability in terms of price of the product in the end. So based on this context, we have the hypothesis that it's possible to access pre or harvest the yield and quality spatial variability using high resolution soil survey and remote imagery. And as I said, one of the objectives is to explore how apparent soil electrical conductivity and hyperspectral imagery can be used to predict the spatial variability of grain yield and protein. So that's one of the goals of using this data. Coming back here, as I said, our headquarters are here, but the wheat region is there. So the farmers field that we are having the experiment is in Ciudad Obregón, is roughly around here. And a little bit of how we build up the methods of the experiments. We have here the Ciudad Obregón, we have Simits station over here, and we are lucky to have a landing strip line just beside the station. So this landing strip line is due to sprayers, sprayers company that it has there. So we don't own an aircraft, we pay for hours of flight, and then the owner of the aircraft allowed us to make 2 holes on the floor to put our sensors. And this actually, I say that we are lucky about that because this gives, like, logistically we can be serving an area around here without any problem. in a weekly or sometimes bi-weekly basis, depending on the pilot schedule actually. And the experimental area just here, just beside the CMT station, right? About the experimental area. So we have 2 blocks of irrigated wheat, each one with 40 hectares. They were sowed on beginning of January 2014 and harvested on mid-May 2014. Field measurements that we did. Previous sowing, we went for a high-resolution soil survey using EM38. So we connected the EM38 sensor with an RTK system, and we built this wood sled. So we drag it through the field, capturing 1 measurement per second. That's why we call high-resolution soil survey. These dot points on red tones, these all, each point is one measurement of the M38, so we made all these pads. We made a target soil sampling, so based on the M38 spatial variability map, we target some soil samplings with a high density quantity of soil samples here in this block, around 100 points, and by purpose with just a few points over here, according with the range variability of the sensor, the response of the sensor. We allocate like 15 points more or less over here in this block. We did some tissue sampling on GS31 stage and flooring on the same sampling points. And the flight campaign consisted like flying 1200 meters above ground, yielding 1 meter pixel resolution with a micro hyperspectral sensor that ranged from 400 to 850 nanometers, split it into 250 bands, and a thermal FLIR camera. And we flow during the crop cycle, and we try to flow weekly, but as I said, sometimes it wasn't matching with the pilot scheduling. So weekly, sometimes bi-weekly, and in the total we got 10 flights through the crop cycle. That's our platform. That's the airborne. So it goes the pilot and it goes a research assistant to be handling with the turning on, turning off, and monitoring, making sure that we are acquiring the data. And this in the corner we have the hyperspectral, the micro hyperspectral sensor, and the thermal sensor. It's called micro hyperspectral because it's a hand size. So it's possible actually to put on board an UAV, and there are some researchers that are doing that actually. So within a flight we have both information. And in the end, before harvesting, grain sampling, pre-or harvesting for yield estimation and sending the grain for protein analysis. Here's some mapping and data mining that we are having by now. The M38 map, spatial variability map that we built with the raw data after local variogram kriging. And one curiosity about this map is like this trend here crossing the 2 blocks. That was really funny actually, because I have the opportunity to talk with the farmer and asking him like the historical of the area, what happened there. And he told me that on his dad's time, it was a irrigation channel here that was crossing both areas, yes. So that was like 10 years ago, more or less, or even more. That was a really good feedback in my view, because we get to understand what is happening in the area. Each dot here is where we make the sampling, soil sampling and tissue sampling, grain sampling in the end as well. So detail about this grid sampling is like we did the 100 points, but it's split it into 2 strategies. 50 points, half of it we made it totally stratified according with the response of the sensor. And the other half we did in a regular grid, but taking off 10% of the points and allocated closer in different directions to the original grid. This for getting a better, robust modeling of the variogram in the end. So this, okay, area B and area A, just to locate you guys. We have our time series of hypercubes. So spatial and temporal resolution of 10 images starting on 14 February 2014 and going up to May 2014. So we started by purpose like around the GS31 stage, which is a really early stage, and it's where if we detect some deficiency on nutrient and we can go for corrections and we can make some interventions regarding yield. And at flowering stage around the end of March, beginning of April, where we may be able to make some corrections regarding protein. So again, each of the images with 250 wavelengths in a time series of it. Okay. This is the yield map. So this yield map was done because we were able to collect these 100 points over there, and here just 15 points, so it was represented with these circles. What is interesting about this yield information is like the minimum yield and the maximum yield that we got in the area. We got like 4.6 tons per hectare as the minimum yield, and maximum yield 8 tons per hectare. So we see that there is a big range, right, among the minimum and the maximum. So then, starting some data mining, starting to understand what is happening there. We went through the whole images and we extracted the wavelengths, the reflectance for the minimum yield point and for the maximum yield point. And here on this graph, we have like on the green lines, we have reflectance extracted for the highest yield point, and the red lines, we have the reflectance extracted for the lowest yield point. Dashed line represents the GS31 stage, so the first flight, and it's getting darker according with the crop cycle, as the crop cycle advances. And the highlighted here, highlighted green and highlighted red is the flowering stage, so what we consider the peak of vegetation within the area. This gap here is due oxygen absorption of the sensor, so it's a noise actually that we just extract before whatever the data analysis that we go through. And what is interesting to see here is like visible on the visible range, they are following the same. Just like in the really end, we see some difference of reflectance between the maximum and the minimum yield. But then in the near infrared, we see the difference on reflectance for even on early stage, these two dashed lines, or in flowering stage, which is the peak of vegetation, we see this much higher, much more attenuated, which is nothing new actually, because if you think about NDVI that has been explored for a long time already, it's used in near infrared and red band, and if we promote a range variation within certain area, you can get a really good relation with NDVI and biomass or yield, right? But what is good to see on this graph is like, okay, so we are having something regarding the state of art. It's respecting the state of art, right? Because it's not just flying, it's about radiometric calibration, geometric correction, atmospheric modeling calibration, to have a full mosaic in the end to be able to extract some information and then go for the data analysis. So it's not just flying and getting the image. There's a whole process within that. But anyway, this is telling that, okay, we are on the right way. Here are some correlations, some PCAs and some modeling with yield. At this step, We just played around with yield information as responsible variable. On these graphs, we have like the first to 10 is the first image on February and the last image on May. And we have the raw reflectance correlation between yield and raw reflectance, sorry. And these on the y-axis is the correlation indices. And this dashed line, which I'm not sure if you guys can see it, but it's the significance interval, okay? So we see that the visible range on the first beginning is not really significant, and then when we get close to flowering stage on the 5th and the 6th image is negatively correlated with yield, near infrared positively correlated, many of almost on all images, but at a certain stage, like visible information is not really useful actually. And so going through some PCAs and modeling, by now we did two approaches. Like as we have like 10 images, we concentrate those per image. We applied PCA per image, and we concentrate those 250 wavelengths into PCs, right? And then we selected those PCs that were accumulating 95% of each image. That was enough, 2 PCs per image was enough to accumulate this 95% of variance. And then we used this information to apply a subset regression approach with a maximum of 6 variables. So PCs per image against yield. And then in a in a selective process, we go like maximum up to 0.55 of adjusted R squared with these PCs, with certain PCs of certain images, right? And this was another approach that we did. As we had this time series of hypercubes, we decided to generate the PCs by wavelength. So each wavelength we had repeatedly like 10 times because it's 10 images. So we concentrate those wavelengths into PCs. So we generate PCs for each wavelength. And then we choose, like we just drop off the 18 values lower than 1. And we got these PCs and we make the correlation with yield. How was the behavior of that? So we see on the first PC, we see like, again, visible, negatively correlated, around 0.4, and near infrared, positively correlated on the first PCs. The second PCs, on visible range, nothing, something on the near infrared. We have some which might be some noise here. And on the third PC, some of the visible range, like on the blue and green, highly positive correlated with yield, and near infrared not that much. So we can see that this information might be complementary of both of them. Using these PCs, we went through like different approach for modeling. We applied partial S squares. We went for random forest, and most of them getting roughly 0.5 of adjust R squared on cross-validation. And then artificial neural network, 0.99. And then, well, whoa. By purpose, I put this, like, take care. It's clear that it's an overfit, so it's something that we are aware, and we are just testing different methods to see what we can get from that. That was mainly reflectance, so just dealing with the raw reflectance of the sensor. And now we went through generating the vegetation index, like what we could be doing with the vegetation index. Besides NDVI, we have the time series of NDVI images here. We calculated other 40 different vegetation index. And then we went through similar approach for modeling, checking the correlation and everything. Here just a bootstrapping interaction of correlation between yield and NDVI. So we have the histograms of the coefficients of correlation and the p-values. And what we can see is again around flowering stage. So the last image of March, the first image of April, we get the highest correlation. It's 0.5 here and 0.46, 0.38, 32, something. And we see that at flowering stage, it's the peak of vegetation, as we know, and is where we are getting better results regarding correlation with yield, right? Here, just graphs of all vegetation index. Each box here is one single vegetation index that we generated, and on x-axis is the images, and on the y-axis is the response of that vegetation index for the highest yield and the lowest yield information of the area. So we see that some of them are having like a non-difference from the highest and the lowest. Some of them are having some, we can see some difference in terms of behaving, in terms of response. So just exploring, just trying to understand what is happening, and then in the end, actually, if you go for whatever the method for variable selection, those guys here are going to be dropped off for sure. And translating these into numbers, like checking the correlation, this table here is, we arranged the correlation index of vegetation index and yield into a decreased order, and then we start asking, okay, how consistent is these correlations across crop cycle? Which are the best vegetation index across crop cycle, and which are the ones that are persistent as the best ones, right? So using like a simple rule, like selecting the top 10 vegetation index that appeared at least within 5 images, we get into these guys here, like EV, RDVI, TVI, MTVI 1 and 2, and Semi-Arid 1 and 2. So these are one of the things that we are checking. Challenge that we faced. Well, this presentation I gave in a workshop that was from STAR. So the idea was to expose the challenges also about the experiment, right? So on field, simultaneously deal with farmers' activities and field measurements. That's classic, no? Weather, windy, cloudy, raining. All these are limitations regarding flying. When we are thinking about the imageries, those are things that we cannot control, and we need just to respect, and that's it. Logistics regarding pilot scheduling, GCP within crop field, ground control points, because we need to put ground control points, like physical marks that we know the georeference of that marks to be able to make the auto-rectification of the images. When we are dealing with this kind of field, which is, there is no plot, so we need to build some ground control points within the crop field. That was a challenge. For irrigation control, like regarding stars, we are dealing with water management, and the control of furrow irrigation is quite tricky. It's not that simple. And if you are talking about non-laser leveled field, that's more tricky. Yeah. And in ops, At CIMIT, we are looking for an online database for sharing, manipulation and visualization, extraction of the data. We are generating these tons of images, and we are looking for a platform to be like to be able to share these, and owners of experience be able to access their experience and be able to do some simple manipulation and extraction of data. Big data, so infinite ways to analyze it. That's something that this is driving me crazy actually at Office. Like you have tons of ways to analyze this kind of data, and as far as you are getting, you are discussing with people, you get more ideas, and this is something that it's difficult. And time for analyzing all this. Yeah, that's one of the things. Some insights and outlooks that we had by now. We saw that the data set showed reliability with consistent brief results respecting the state of art of remote sensing, right? Reflectance from the highest and the lowest yield region showed a difference during crop cycle, mainly at flowering stage and in the near infrared region, which is nothing new, but it's good to make the proof of this, right? Top 10 correlations which appeared at least in 5 images. So about consistency. EVI, Emikari 1 and 2, MTVI 1 and 2, RDVI, and TVI. And actually, if we go back to that graph, we see that some of them are having same behaviors actually. Emikari 1 and 2, like they are telling the same story. So I guess if you go through the modeling approach, this one of them is going to be just drop out. And outlooks, what we are expecting: detection of crop nutrient, maybe water stress beyond nitrogen, in time to manage it. The goal that one of them that I'm most interested in, the predictive of yield and grain protein spatial variability previous harvesting, so aiming a selective harvesting strategy. One of the things that we have in mind that we might don't need 10 flights during the crop cycle. We might be able to do the same, to have the same power of prediction with just 2 or 3 flights in really key stages of the crop. And another thing is that we might don't need a hyperspectral signal as well. We might be able to deal with just 2 or 3 or 4 wavelengths that we detect that are the main ones, giving some power of prediction, and then we don't need to invest for a hyperspectral signal. Questions that we have: how consistent this is over crop seasons? Like this is one crop season, so this is going to continue like the same thing for the next year and the following year. So that's something that we have in mind, and for being able to determine a robust algorithm to achieve these objectives, we will need to see this across crop cycles, in different crop cycles and conditions. And again, how many images do we need across crop cycle? For sure, I have in mind that we might not need like these tons of hypercubes of the area. So yeah, basically that's it. Thank you very much.
Okay, thanks very much, Francelino. So we'll open up for questions from the audience. Maybe I can start and then others can come in. You didn't explain what the EM38 was actually sensing. So the work we did in the Mali in the past was salt, because salt was dominating what the signal was doing. But maybe explain to us what the EM38 was detecting in this case.
Okay, good. Well, the principle of EM38 is mainly the electromagnetic induction. So it's a field, a capacity field that is emitted, and in one coin and in another coin is receiving this magnetic field. And the key factors that is responsible about this response of this sensor are mainly, I could say, physical properties maybe, like salinity, clay content, pH, soil moisture. I see as it's a matrix of factors that is influencing on the response of this sensor. And sure, depending on the scenario, if you have salinity issues, the salinity is going to be driving the response of this signal. If you don't have salinity and you have like a high, you have moisture, like the moisture is going to be driving, but I see as a matrix of factors that is influencing. And on precision ag, mainly we use this kind of information jointly with yield information, for instance, or it can be jointly with images or farmers' knowledge, building like what we call management zones, for instance. That's the use of this sensor in precision ag. One of the use, sorry. Some people are using for lime application as well. And yeah, basically it's this. I'm not a soil scientist. Be aware about that. But yeah, this field of expertise I see as multidisciplinary. So. Yeah, actually I skipped that information. Sorry. We got like a on horizontal dipole we got a point negatively 0.24, and on vertical dipole we got 0.32 negatively correlated with field. Yeah, yeah. But yeah, well, my opinion on that is that this variation is good actually, because we need just to understand the reason of this variation, because as you said, like this 100% difference of yield, that's where we're going to be able to discretize, like to detect and to be able to go for some modeling, I think. Because if you have like a homogeneous field, which to me is just impossible to have, if the hyperspectral signal is telling things about the canopy, and the canopy is behaving according to soil spatial variability as well at certain point. And I don't know, my opinion on that is that we need just to deal with this spatial variability and understand what is happening. And actually the soil analysis of that points, it's with the purpose to try to explain later further why that was like a lower yield and why that was a higher yield. Because actually the hyperspectral images, we're going to be able just to tell the story across crop cycle, but without understanding the reasons, right? And yeah, my personal opinion on that.
Other questions?
I was curious to know what, if you reflect this in terms of costing, how much is the workout per hectare for this entire exercise?
Cost?
Yeah.
Well, the sensor is our sensor. Like we are owners of the sensor, but and we play hours of flight of the airborne, and I guess it's like $5,000 a package of 20 hours of flight, and that's a lot actually. You can fly a lot with 20 hours of autonomy, and in that case, like it's with like flying at that high and yielding 1 meter resolution, we needed on that case 2 PEPs, so we passed it 2 times on the area, and honestly, like it's the time demanding on the setting up of the equipment once you take off, it's quick. Yes. So that's the cost. But about sensors and all those things, I wouldn't know to tell you.
But longer term, I think the question is, longer term, what would be the application? So you're trying to set up, this is a generic way of doing it. Maybe in the long term there'll be commercial services available to provide sensing and then related to some management input.
Yeah. Well, I see that possible actually, and again, coming back, I would go back to my comment that we might don't need a hyperspectral signal, right? Like I see this as a long time frame in terms of research, and maybe at the end we see that the wavelengths that we are needing there is wavelengths that we can find in satellite sensors that are already in orbit. So this might happen, I guess.
Are you using any Hyperion data about these areas? Hyperion data, Hyperion narrowband, hyperspectral images from the satellite NASA data set.
I didn't get your question. I'm sorry.
No. Are you using any airborne data sets, or are you using any Hyperion data sets? Hyperion, that satellite images.
Satellite image.
Yeah.
Actually, no, that's a hook for a comment. We we have a product that we generate, which is called GreenSat. It's a system based on Spot 6 images, and we have it online. I can show you guys the address later. It's for nitrogen management. So one of our scientists that is more related with crop nutrition, he made calibrations using GreenSeeker, an active crop sensing. He made calibrations using this sensor for nitrogen management, and we upscaled this information into algorithm using spot images. And at this experiment, it matched, like one flight, it matched with a spot image that was in that region, and we made just a comparison. But we are not using truly satellite information with that. Yeah. I don't know if I answer your question.
In future, is somebody it has to be commercialized to use this kind of technology. So, whom do you expect to be the main users of this kind of data to purchase from the commercial units or whatever? Whom do you expect to be the main users of this kind of data, which can help in commercializing?
Or who? Who would be the users? Farmers, yeah, service providers, and because, well, we need to be realistic that this kind of high-tech stuff, many of the farmers just cannot they afford it. But service providers and governments, and I think that might be feasible. And on your areas, like you and Santiago, for instance, we have been discussing like a landscape assessment, for instance, to understand what is happening. And this might be one application as well. And who, I would say, service providers and government, yeah. But mainly, like, sure, farmers, targeting to farmers.
So you touched on spatial variability, and Vincent wants to minimize it, but you want to maximize it. Can you say something about whole-of-block experimental approaches and whether they might be applicable?
I think so.
Yeah.
Yeah,
Maybe you need to explain.
I think it's really interesting approach actually, and just correcting, I don't want to maximize, but I just want to be aware about this spatial variability and to understand what is happening. That's the point. And about this approach, I'm not really familiar to, but I already read, and I think it's a good approach for farming field experiments. And yeah, it's about capacity building and things like this to be able to apply, because also statistically it's not that simple. We know that it's really complex statistics behind, so yeah.
I mean, my aim is also to maximize the difference, but in a way that I know. So in other words, I mean, well, at a 40-hectare level, I mean, you're going to have some variabilities. I mean, so
Yeah, depending on scale,
that's
right?
life, no? But I mean, you can work at scales where you can limit your variability. You'll always find variability with the M38, but within ranges where you don't have sort of
Yes,
effect. I mean, we have measurement in those fields here where we have variation, but I mean, very limited variation in variation in the EM38 reading, but little variation in terms of what we measure.
Yes.
So for me, the approach is really to have variation in a way you control and have a little bit of sort of few entry points on what we think would influence your spectral indices. I mean, simple things, nitrogen, water. So have you thought of having, for example, block where you drip irrigate, block you keep dry, block you fertilize, and then sort of look at the indices you measure, and then okay, when I've got a treatment like this is what I measure.
Yes.
And so to get back to your sort of unknown variation in a more sort of informed
like
way.
promoting. Yeah, and
So
no, I fully agree that
the
would
use of the whatever sort of imaging is really about knowing what we measure.
not knowing what you are
with
measuring,
regard to
definitely.
plant biology.
Yes, and actually that one thing that for breeding plots, for instance, and physiological plots, it's something that we are looking for, and for instance, to make a high resolution soil survey with M38 before the experimental design, to understand what is happening there and putting your blocks in a way that you are decreasing this variation. That's a topic that is happening there as well, and but then once we talk about farms field experiments, then I see that the whole block designs and those things would be approachable. And but I have in my mind also that sometimes we are promoting a range variation that if we go for a real field, we don't have it. And then I guess that's the point that we will need some robust approach to be able to capture, I think. Yeah.
One question from outside of campus, Dr. Das from IIT KGP. I was wondering about the high R2 from ANN modeling. Did ANN capture the signals better than species?
The high R squared, he said about?
High R2 from ANN modeling, ANN.
Okay, yeah. Well, to me...
ANN capture the signals better than PCs?
Actually, the PCs was the input on that approach. And I'm not a really expert on artificial neural networks, and to me it's a bit of black box. And if we go through the model, we won't understand the weights of the variables, what happened there. So that's the reason actually I put like, whoa, like take care, because it's not just about having a high R squared and not understanding what is happening, right? Definitely. And actually that was just tests. Well, why not to test artificial neural network? And to me that is clear an overfit actually as well, because that's one of the issues we are facing. Like we are having like a really horizontal metrics, and we need to decrease the dimension of these data to be able to avoid these overfits.
There was one more question from KPC Rao. Considering the most significant correlation occurred at flowering stage and beyond, how useful will be this information for management?
I didn't get the question.
Considering the most significant correlations occurred at flowering stage and beyond, how useful will be these information for management?
Well, as I said, like it's known that on early stage the interventions that we're going to give in terms of nitrogen management will be reflected on yield. And at flowering stage, any intervention that we might go through, it's going to be reflecting on quality, on grain protein, yes. And but it's not like 100% of the intervention that we'll be able to capture, I guess. In terms of crop management, I think if we detect some lack at flooring stage, we would be able just to correct something regarding the quality of the grain. Yes. That's what. Sorry, just finalizing that. That's like one learning from crop nutrient scientists from Chile. Yes, yes, I did.
Yeah. So among the different vegetation index, I think NDVI is used more frequently than any other one by the researchers. But I see that some other vegetation index are doing better than NDVI. So what is your comment on that? At least recommendation for researchers.
Well, I think as far as we are dealing with even you don't need to deal with hyperspectral. If you're dealing with multispectral signal, you're already able to go further to other vegetation index because we understand the limitations of NDVI and in terms of ground reflectance as well and saturation and things like that. So I don't see why not to explore other kind of vegetation index that are on the literature regarding water content of the plant or chlorophyll content of the plant and so far. So if you have a multispectral signal, I think it's worth to explore more. I don't see why not.
Sartajit MC, thanks for the nice presentation. This is Sartajit from ICRISAT Mali. What would be the best way to invalidate the approach, PCA or ANN models?
Again, please.
Thanks for the nice presentation. This is Sartajit from ICRISAT Mali. What would be the best way to validate the approach, PCs or ANN models?
ANN models, artificial network models. I don't know.
Okay.
It's a matter to investigate, to explore. Yeah. Like, and actually, well, I would come back to that comment. It's like we need to see how consistent this is over crop cycles. Like, it's not just with 1 year that we'll be able to say, okay, use this as a protocol. You make the data analysis, PCA, and that's it. I don't see like this. I think the data mining is really important in this process, and until get concrete answers and things like this, I think it's a long time frame. Yeah.
I think we have to pull up there. Muchas gracias from ICRISAT. I think there's a possibility to talk to Francelino the next day and a half. I think particularly Vincent, your group is going to interact. So please talk to him immediately afterwards and organize some times. Same with Santiago. I think there's several people who are into household modeling and typologies that will talk as well. So thank you very much, and we appreciate your time.